Hi everyone, welcome to my talk about embodied AI. So this is the timeline. I will briefly explain my background and my research topic. Then we will move to the embodied AI. So I will give a brief definition, the common dataset and tasks, and some state-of-the-art solution to this problem. Finally, we will see the what's next of embodied AI, so the tasks, the model, and the combination of them. So I obtained my bachelor degree here in computer science here in Verona. My master degree is in computer engineering for robotics and smart industry. And now I'm doing my PhD program in artificial intelligence with Polytechnic of Turin and the University of Verona. I'm in the second year, and my research topic is called Active Vision for Intelligent Robots. So what is, first of all, active vision? I think this is a great definition. So how we can optimize the efficiency of the downstream tasks by leveraging information that we gather during the rollout of the episode. In this figure, we can see some examples. So, for example, in 2019, we had the point-to-go navigation, so how to reach a specific position inside a home. And with Habitat 2.0 in 2021, we introduced robot manipulation, and in 2022, near and perfect mobile pick and place. So active vision in this sense is how to get an information to complete this task efficiently. So, for example, if I have to find an object inside a home, if I have to find like a sofa, of course, it is more efficient to explore first the living room instead of the bathroom. So we can use this information, this common sense to improve the navigation. So first of all, what is embodied AI? I found this definition of embodied AI in the Habitat website. Later on, we will see what it is. And I think it is really great. So embodied AI is the science of and engineering of intelligent machines with a physical or virtual embodiment, typically robots. And the embodiment hypothesis is the idea that the intelligence emerges in the interaction of an agent with an environment as a result of a sensory motor activity. Later on, we will see this embodiment hypothesis and its relation with LLMs and world model. As I said before, this is a timeline of the common tasks and dataset that we use in the embodied AI field. So we start with a simple navigation problem like point-to-go navigation, and now we have with Habitat 3.0, that is the late arrival in the late 2023, called social navigation. So we want a robot to follow a human while maintaining a safe distance with a human. In the right plot, instead, we can see how the embodied AI is going rapid field. For example, this is for the Habitat Challenge at CVPR, and we can see that during the year there is a continuously growing team that is working in this field. So it's pretty crowded now. Okay, so differently from other field, in the embodied AI field, we have two types of dataset. One is called the scene dataset. For example, Matterport 3D and so on. So it's the environment in which the agent can move. And then we have the task dataset. So for example, the embodied QA, visual language navigation, object navigation, and so more. Of course, we have a lot of simulator, and the combination of these three components, like the scene dataset, task dataset, more importantly, the GPU's acceleration is fundamental for the development of this application. And I put this slide to like show an example of a scene dataset that is the most common HM3D. As you can see, it resembles a real home. It's scanned with some cameras. Matterport is a company that is doing this product and released this home. They are composed by multiple floors. They are also very, very large, and the quality of the scannings are real good. This is an example of navigation inside the home. So you can see that the agent is moving inside the home while doing low-level action. On the right, we can see the top-down map representation of this particular home. So this is just to give you an example of what are the dataset. At this link, you can find you can find all the dataset if you want. Okay, so now, as I explained before, I will briefly introduce the common tasks. So for the point navigation, the agent must navigate to a specific location. For example, go to 100, 300. And the only input are the RGBD, so RGB image and depth information, GPS and compass sensor, okay, and we have to arrive at a specific location. Yeah, okay, so in the latest 2019, the current SOTA was like 80-90%. So we were unable to reach 100% in this can be also simple task. Okay, then in the meta, that is the one that basically publish more paper on this type of field. In the iClear 2020 paper released a paper called DD-PPO, Learning Near Perfect Polygon Navigator from 2.5 billion frames. And I find the abstract of this paper really cool because basically they wrote, we leverage the scaling to train an agent for 2.5 billion steps of experience, the equivalent of 80 years of human experience, over 6 months of GPU time, training in under 3 days of world clock time within 64 GPUs, okay? And this massive scale training not only set the state of the art on habitat autonomous navigation challenge, but essentially solved the task. So for the first time, a company, a research, was able to solve a task that is, for example, point navigation. And on the right plot, we can see that basically the validation accuracy SPL, validation metrics SPL in this case, was particularly high, like 99.9%, okay? So basically they solved the task. And this is require a new training algorithm, distributed decentralized PPO, using a lot of GPU, of course, but for the first time, we were able to solve a task. Other pretty common tasks are instance image navigation. So the input to the agent is a particular image that is disentangled from the agent's camera. So we can changing such as the height, the look-at angle, and the field of view to reflect the case that a human take a picture of inside the home and want to retrieve and want the agent to go to that particular location. I think the most common task in the embodied AI field is visual language navigation. In this case, we have an agent is given a first-person egocentric vision and a human-generated instruction. For example, go down the hall and turn left at the wooden desk. Continue until you reach the kitchen and then stop by the kettle. In the GIF that you can see in this slide, you can see that there are NP3D simulator and habitat sim. This is, of course, a huge difference in simulator that Habitat introduced. So we were moving from a discrete simulator, so a simulator that basically give you the nodes on which you can select to perform the navigation, to a continuous environment. As you can see, Habitat is the agent perform low-level action. For example, turn left 15 degrees, turn right 15 degrees, and so on. Instead of teleporting between nodes. And this is very, very challenging to do, to train agent and to perform evaluation. Yeah, the challenges in this type of tasks are basically the instruction grounding, so how to understand the content of the instruction, the vision and language alignment, so what part of the instruction I've done, what are the rest to do, and the continuous environment itself. There are basically two types of model to solve this task. One is the sequence-to-sequence model. So Like, for example, I extract embedding from the image, then I extract the embedding from the instruction. Images are processed by recurrent neural network and so on. Another type of solution is the waypoint predictor. So we train agent to predict nodes, basically simulating a discrete environment. And then we use this model to predict the nodes inside a continuous environment and decouple the navigation from the low-level action. So I can choose which node I have to navigate to in the environment, and then basically have another module that can reach that goal. And this is exactly what the state-of-the-art visual and language navigation model is doing right now. It's called BVBERT. It was published last year at ICCV. And basically, it is composed by three modules. So graph-based topological map equipped with a global action space. I don't know if you can see my mouse. Can you confirm this?
Yes, we can see.
Okay, perfect. Okay, in this case, you can see this is a top-down map representation of the home. This is the instruction, and this is the global topological map. So these are the nodes that the model predict. The local metric map instead integrates a visual feature from the current node, from the nearby visit node. It merges them, and it projects them into a board view map representation. And later on, these features are fused together with cross attention using a transformer. The third component of this module, of this model, is really, in my opinion, the key to have a good result on this task is the pre-training tasks. BVBERT uses three pre-training tasks. For example, mask language modeling. It resembles like BERT, so how to recover word given the surrounding words and the hybrid map. Hybrid single action prediction, that is, which is the next action I have to do, and the masked segmentation imagination. So they masked cell, and they want to predict the classes that are in that cell. Of course, in the bottom row left, there are all the references to if you want to learn more. I also want to introduce my latest work, that is mind the error detection, the detection and localization of instruction error in visual language navigation. So all of these previous agents considered instruction to be correct. Instead, we take another direction. So we consider instruction that basically could be wrong, because in practice, this is what can happen. So everyone made the mistakes. So in this paper, we basically benchmark visual language navigation in continuous environment agents, and we found that up to minus 25% drop in success rate. Okay, so it is a huge drop in my opinion. We proposed the task of instruction error detection localization, and we propose also a model called IADL to detect and localize this error. Here we can see two things, in my opinion. So the first one is that the SOTA model from the left to the right, the more the SOTA, the more the performance are higher when the instructions are correct, the more the performance are lower when the instructions are wrong. And this is because actually the agent is really following the instruction. Instead, if you start looking from the right, so sequence to sequence, CMA, and so on, you can see that basically the performance are the same, because the instruction was not so important to define the navigation performance. Okay. This is a picture of the model we designed. So we took a frozen policy pi, that is BVBERT in this case. We give the instruction, correct or not. We extract the visual feature from the rollout, and then we use two encoders, so a panoramic encoder to produce visual feature, and a language encoder to produce language feature, of course. We fuse together this feature using a cross-modal transformer. And then we use the CLS token to and give them to specialized heads, FD, this detection head, and the FL localization head. So with the first head, we can predict with an anomaly score if the instruction is correct or not. And with the second head, we can predict the location of the wrong word. Basically, then we use this model on the standard dataset, and we found that actually the standard dataset contains some error, and it should be filtered out to basically have an evaluation more fair with other paper. A follow-up work is this one, so interactive instruction error detection localization, in which when we detect and localize a specific error, we can request the user with the correct one. And if the localized word is between a range, we basically reload the embedding in the agent and perform the navigation. And we saw that we can improve the performance. We also propose a new metric for every paper that is doing some interaction navigation. It's called SIN, so success weighted by interaction number, that combine in a single word, in a single metric, sorry, the success rate and the number of interaction. And this metric, if you are, basically are reading some paper in embodied AI, it resembles a little bit of the SPL, that is the most famous metric for navigation performance. The last one is the object go navigation. So we are in a known environment. We want to find a particular object, okay? For example, find the bed, find the chair, find the oven, and so on. Typically, in the dataset that are commonly used, the set of goal is limited. So in this case, there are 14 objects, 15 objects that we can found. And yeah, also these are real world implementations. So the model are trained in the Evita sim and then ported to the real world. Okay. So if you have some questions, please ask, or I can continue. All good?
Yes, continue.
Okay, top. Okay, so now we can see basically what are the next model, the next task that we are considering in the literature. So this is the latest work from the Meta AI team. It's called OpenAQA, so embodied question answering in the era of foundational models. And the goal is understanding the environment well enough to answer questions about it in natural language. So if I gave you a short video, like 15 seconds of an exploration inside the home, and I ask you what color are the blinds, you typically are able to answer white and so on. Or for example, what color are the sofa chair in the living room? You can answer that, okay? And yeah, for the human baseline, this is pretty high, 86%. And basically, what they found is that current models are not working so good. For example, the latest GPT-4 vision model is basically doing 55% in this type of evaluation. And in this paper, they propose two types of tasks. So one is given a video, you have to answer the questions, and another one is called active exploration. So I gave you the question, but I don't give you the video, of course. So you have also to navigate into the scene to find that particular answer. And this is very different from the old question answering tasks in this field, because in the previous work that were doing question answering, the questions were templated. So basically close set, let's say, what color are these objects and so on, and then are created. In this case, we have a lot of answer typical, a lot of questions like object recognition, attribute recognition, object state recognition, object localization, spatial reasoning, functional reasoning, and word knowledge. Also, in this case, we can see the number of episodes for the episode memory AQA, so the one that I gave you the video, and active exploration AQA. Another task that I see a lot in this type of year is fusing LLM, so language model, with physical grounding. So don't know if you remember what I said in the initial slide, the embodiment hypothesis. So real intelligence is basically when we also interact and we make experience in the environment, okay? And LLM actually are not doing that. There are also a lot of also Nobel Prizes winning people that say that LLM, the current limitation to language model is that they cannot interact with environment, so they can't ground in the world. A cool work that I saw is a 3D vision language action generative world model. So what they have done is basically they took an LLM and they enlarge the tokenizer, so they can also input images and point cloud into the model. So you can see that we have multiple images. The prompt is the initial scene is scene, so this is the scene embedding, and I want to ask, find some snack for me. And the 3D vision language action model basically say this. Sure, I should go to this type of location inside the image and pick up this object. And the cool thing is that they also enlarge this type of model with a different diffusion model. So I can also generate the final state of my action. So if I want to grab the chip bag, I know that this will be the result. And I can generate the image and the point cloud, okay? And so from the 3D feature, I can execute now the action, and I can retrieve the robot control to perform that action. So this type of movement. By the way, these require a lot of GPU, of course, but the results are really cool. I encourage you to see the website. Another task is that, as I previously said, object navigation has a closed set of target object. Now we want to perform object navigation with open set, so multiple object, unlimited maybe. And also we want to do it in a zero-shot paradigm, okay? And this can be done with using some very old type of navigation that is frontier exploration, is by the 80s or the 60s, I don't remember exactly, and improving it with current vision language model, okay? And for example, in this case, we basically, we are doing frontier-based exploration, but the frontier are, but while we are navigating, we are embedding into the map a score that is derived from this called value map, and the score is derived by vision language model, and the similarity between the image and my input. So if I have an image of a bathroom and I want to search for VC, obviously the score will be higher than when the image is basically a kitchen. Okay. So then we select the frontier node with the highest score, and this model is very effective. Indeed, we can see the result with other zero-shot model in this part of the table, and we can see that the success rate is basically 84% for the success rate, and SPL is 52. SPL is a metric to combine the success rate and the length of the exploration. So is to combine how I was efficient when finding the object. And the author compared this work with a some supervised model like Pony, SMX, and so on. And indeed, you can see that the results are actually higher than the trained one. Okay, so you basically have no training. You can't overfit to the data set. The only limitation is your sensor, your object detector, and so on. And indeed, this is, we don't have also seen to real transfer because we don't train. And this was tested on the Spot robot by Boston Dynamics. And fun fact, when we select the node, how you can navigate into that particular location using the point navigation policy trained before with the PPO. So that model was really useful because now we can use that as a black box and focus more on the action selection than the low-level action to navigate to. Another cool task is now GoatBench, a benchmark for multimodal lifelong navigation. And basically, in this paper, we want to, it's not restricted to a predefined set of categories, and it is lifelong. So if I'm starting this position and I'm exploring this, and then I found my recliner chair, and when the input is the white book on the coffee table in the living room, basically, if I'm smart, if I'm building a multimodal map in my memory, I can retrieve this location without exploring that type of zone of this scene. Because I know that the white book is in this location. Another task is to solve visual language navigation in a zero-shot way. And a way to do this is by using some really huge LLM. And you can see that these resemble a little bit what BVBERT is doing. So we have a global map guided prompting. So we construct a high-level map. We can see the content of the nodes, and then basically we can prompt the LLM to choose the next node to navigate. Yeah. Okay, now we are basically at the end, so we can see a little bit more some cool latest research. So AI loves robotics, exponential usage of visual language foundational model. I wrote this because, as you can see from the previous slide, we are now we are using a lot more and more the visual and language foundational model to perform the tasks. And the key is to use that model without training, of course, because we don't have the resources. So we have to combine them in a smarter way to use in a zero-shot fashion. This is Seiken from Google, and they basically perform this task using an LLM. So the prompt was, I don't like caffeinated soda, can you bring me something else to drink from the table? And the robot basically said, the user asked me to bring a drink that isn't caffeinated, I will bring the water bottle. And it can, and this agent can plan what to do, can reach the target object and retrieve the bottle, also with the grasping. Okay. It's a bit slow. Okay. Another usage of LLM is, of course, how to use them without fine-tuning, and we can do it with adapter. This is a paper from last year. It's called LM Drive. So using language model to drive in a closed loop scenario machine car. A closed loop is when you are basically predicting the action of the steering wheel and the accelerator and the brakes. And yeah, of course, we have to extract embedding from the instruction, extract embedding from multiple image and leader, if we have them. And of course, now we will see more and more this type of notation in paper. This is freeze. We don't train this particular module inside the model. And when you see fire, is because it is fine-tuned or trained, okay? So in this case, the vision encoder is fixed, is freeze, sorry. We fine-tune or train a conformer. And through adapter, we can basically translate the content of the image to the language model, to the large language model. And then with adapter, we can also get what are the low-level action to perform. And yeah, there are a lot of work in this type of days that are doing driving with LLM. A very cool work, in my opinion, is also Gaia 1. It's from Wave. It's an autonomous driving company. And I'm connecting to what I said before with the hypothesis, embodiment hypothesis. So here we are defining the world models. Don't know if you heard about it, but our model is a model of the world that animal and human develop through interaction and observation. Some people speculate that LLM doesn't have this. And world model are the basis for the ability of predict what might happen next. Okay, and what Wave basically is doing is that they train a model, a world model that is using video and or natural language prompt to generate plausible feature, not feature but the future. Sorry for the type. And in this case, basically, they can train and generate videos to train the autonomous driving pipeline using a model. And these, sorry, the quality is really low, but yeah. And these are all generated videos. So I can also prompt, I want this scenario, but during the night when it's raining, and the model will output the video on that particular location. So I think in the future, we will see a lot of this type of work to generate some specific autonomous driving condition that we don't have to retrieve from the real world because it's costly and maybe impossible. Another type of work is LLM and robotics. So I don't know if you see this work, but basically it's from a company, Figure 01. OpenAI speech-to-speech reasoning, and it's basically able to perform reasoning using speech from the human and integrating with OpenAI. It's a really cool demo, and it can also it's also to grasp the object, and this is a super challenging task of when using robots. Okay, this was my presentation for today's talks. If we have a question here.
Io avrei una domanda. Ciao. Sorry, in English. Sorry. Just a question. I saw in Estonia moving a lot of small robots running around the city. I know this is a technology. I can send you the link of the producer. I just want to know if you know something about it, or if
okay, sorry, I stopped sharing. Maybe I wanted to see the link.
I send it in the chat.
Yeah. Let me share all my screen. Okay. So
okay.
I can chat. Okay, no, I didn't see that one particularly, but it seems really.
I just saw these small robots moving around the city, so I just want to know if you know it, and if they implement this kind of researches you were talking about today. Thanks.
Okay, so I don't know that particular company and what it's doing, but basically I think that for sure they will be trained in some sort of simulator. And yeah, what type of task are they doing? So are collecting information, or do you know?
No, I don't know. I just
They should be delivery robots, as far as I remember. I remember seeing how do you say, a startup using pretty much that configuration for delivery.
Okay. Yeah, there are also visual language navigation model that try to work outside because, of course, all the work that I presented to you are basically trained using inside the sim dataset. There are other work that are doing that for the outside world. But yeah, so I'm not knowing that particular top company and what are the products, so it's difficult to me to give you if they are using some of this technology. But yeah,
it was just a curiosity, because I immediately thought back to this kind of robots I saw a lot of times. Just this.
Yeah. I will do my research about this. Delivery, okay, is doing some sort of delivery. Okay, cool.
Yeah, I remember seeing some funny videos of their AI going a bit wrong, where they would maybe there was like a non-functioning traffic light, and there was basically this infinite queue of those delivery robots just waiting on and they were making like a super long queue because they didn't know how to handle it, so they just stayed there and waited and stuck. I think in the US, I've been working for longer, I think.
Yeah, that could be a really huge problem. And that's why I think having this type of model that can generate specific training data, because this can generate training data of particular scenario, can be a solution to that problem.
You mean generating synthetic but realistic data sets for handling? Yeah. Generative AI for this is for sure a great thing.
So take a look at the video, these videos. In my opinion, Wave is a really great company, and working on this, you can see the result in a much higher detail. Yeah.
I have a question related to the sim-to-real. So all the work you showed today was related to training an agent in simulation, but is the passage from the simulation to the real world so seamless, or there are some challenges, there are some techniques that help to go from the simulation to the real world?
Okay, so good question, first of all. Okay, for the first one, sorry, point navigation tasks, I can show you. Okay, we have the depth, the RGB information, and the GPS plus compass. And in that training, we didn't consider any type of noise in that sensor. Okay, but this is not true in the real world. Also of the depth. For the depth, if we don't have a specific camera, we have to use another model to predict the depth information. So this could be a problem. Now, the task of point navigation consider sensor with noise, and so this could be a solution to that particular type of a problem. Of course, sim-to-real is not solved yet, and let me show you another slide so we can do. Okay, this particular paper is called Real-World Object Navigation, and what we have done is to train 3 different policies. So one is end-to-end training, one is modular training. Sorry, it was 2. One is modular training. So they train some particular sub-module, okay, like for example, point navigation and so on. And they basically compare the success rate from the simulator to the real world, and they can answer some specific information. So modular, of course, can be more challenging to set up, but can work better in the real world, because if you don't train, you don't have the sim to real transfer gap, because you don't overfit to the dataset. Another solution is to improve the quality of the simulator, of course. So for habitat, the RGB observation are derived from a reconstructed RGB mesh. I don't know if you can actually look at this, but the quality is not so good compared to reality, of course, because compared to other simulator is very, very good. And so this could be another thing to improve, in my opinion.
Okay, everything clear. Thanks.
Other ones?
Before you mentioned some tasks like I don't like soda water, carbonated, but you open.
Okay.
But how is it called, that task? Because this one you talked about is visual language navigation. How do you, is it, what is it, retrieval? Is it?
Like this one?
Yeah, exactly.
Okay, it's a sort of object navigation. Okay, this is not a well-defined task. I mean, you can say it is affordance navigation, like I want some particular object that satisfies my condition. And like I don't give you the target goal, but you have to derive also given the context. There are papers doing that. It's called demanding object navigation, if I'm not mistaken. But yeah, there is no particular name of these tasks.
Okay.
Yeah.
No, because I remember seeing it on some demo from OpenAI, I believe, or something similar, where they had to stack something in the dishwasher. Or so I wonder if there was.
I think maybe this is pretty related. I don't know if they have also other type of demos with the dishwasher. Okay, this is the container of the dishwasher, but yeah.
Yeah.
It's pretty good.
Okay, thank you.
No other.
Anyone else has questions? Otherwise, we can let Francesco go. Okay, I guess then we can let Francesco go.
Okay. So thanks for inviting me, and hope it was clear. Sorry, and yeah.
Thank you for your time, and we hope to see you here again.
Yep, we can arrange another meeting.
With pleasure. Thank you very much, Francesco.
Thank you again. Bye,
Francesco. Thank you very much.
Thank you. Bye. Bye.